One of the most important concepts in drawing a Lewis structure is the idea of resonance. And when I first learned to do this, we did Lewis structures intuitively. We didn't have a nice, tidy 5-step process to getting a good Lewis structure. And so I ended up having to guess where the multiple bonds were, if there were any multiple bonds. And then this idea of resonance was very confusing. But since we've got this stepwise procedure, it makes it a little easier to get started drawing good Lewis structures. And if you know the 5 steps for drawing Lewis structures that I went over in a previous lecture, including like the dot structure for nitrite, which shows how we get multiple bonds pretty explicitly, and that happens during the 5th step of our procedure. So we have a 5-step procedure, and during the 5th step, we often have a central atom that does not have a full octet. If that's the case, where the central atom doesn't have enough electrons in its environment, it causes a non-central atom with a shareable lone pair of electrons to share with the central atom, and that creates multiple bond to satisfy the octet of the central atom. And I'll do another example to illustrate this in a few minutes. But if there's many ways to do this 5th step, if there's different options on who shares with the central atom or how many times you share with the central atom, then you get one Lewis structure for each possible combination that will work out with the filled octet for the central atom. The shareable lone pair, when shared, becomes a multiple bond, or as we'll call it soon, a pi bond to the central atom. And often a single Lewis structure that results from this step will indicate that one bond is shorter and stronger than the other bonds, when the group of equivalent bonds should all be the same length and strength. So a single structure is often misleading and misrepresents the bond lengths and strengths of the different bonds to the central atom. So this moving the lone pair of electrons from a non-central atom to create a new bond is an example of electron pushing, which is a very, very important concept in organic chemistry. So if you master the electron pushing, then you'll be able to write and understand mechanisms pretty well for these things. Alright, so this is a little abstract discussion of, as we do our dot structures, if during the 5th step there are multiple ways to satisfy the octet of the central atom, we execute all of those combinations and we get a bunch of resonance structures. The goal is that the model that we create represents the bonding in the molecular ion as accurately as possible. And so let me go through an example. Carbonate is one of the common polyatomic ions that we should be familiar with. Carbonate has the formula CO3 2-. So let me go through and do a dot structure for carbonate. First step is to determine the number of valence electrons. Carbon, being in group 4, brings 4 electrons to the party. Oxygen, being in group 6, S2P4, brings 6 electrons, and there's 3 oxygens bringing 6 electrons each, and then to get to be -2, you have to add in 2 more electrons to have an excess of electrons and the negative charge. So total number of electrons, valence electrons in carbonate, 18 plus 2 is 20, plus 4, 24 valence electrons in the carbonate. So that's necessary to get the right dot structure. We put the carbon in the center, attach the 3 oxygens to it. Ta-da! Second step's my favorite. Just connect things up. Third step would be to fill the octets on the non-central oxygens. And again, if you've already got 2 electrons near the oxygen because of the bond, we add 6 more to get to 8. Not very difficult. And then at this point, we look to see, after we've determined the number of valence electrons connected with single bonds and filled the octets of the non-central atoms, we see how many electrons we've used: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. So we've used all the electrons we have. We can't put any more on the central atom. So I might like to put a lone pair here and fill its octet, but I can't do that. I do notice that this carbon only has 6 electrons in its environment, so it's not obeying the octet rule, and we have to fix that. Alright, so we can't add any electrons. We need more electrons around the carbon. So what does it do? He forces a neighbor to share. So we can start with the left oxygen and say, if he shared this pair of electrons, and here's where the arrow push comes in, this pair of electrons is going to move from being a lone pair of electrons on the oxygen to being a bonding pair between the carbon and oxygen. And if I do that, then I get a double bond to the left oxygen, and I still have single bonds to the top and right oxygens. So that illustrates the arrow push to move the lone pair to form the bonding pair. So there's the new bond. And now the carbon has 2, 4, 6, 8 electrons in its environment. This oxygen has 2, 4, 6, 8 electrons in its environment. The octet rule is obeyed all along. We're going to put some brackets and write the overall charge, just to make sure the bracket and charge police don't penalize us. But then when I look at the structure, I mean, it looks great. 24 electrons, octet rule everywhere, looks great in some respects. But what it's suggesting is this left carbon-oxygen bond is shorter than the other two, because it's a double bond and the other two are single bonds. But if you know anything about carbonate, you know that all 3 bonds are exactly the same length. So this single structure is misleading in that it makes it look like one of the bonds is shorter. But then, as I mentioned in a previous video, and you probably have heard in the lectures that you attend, the other oxygens could have shared with the carbon as well. So rather than having the left oxygen be the double bonded one, we could have had this top oxygen be the double bonded one. So that's what I mean by a different combination or a different choice as far as during this 5th step of filling the octets of the central atom by sharing pairs from a different atom. We could either have the left oxygen be the double bond, or the top oxygen be the double bond, or if we arrow push this way, we could have the right oxygen be the double bonded one. I had to pause there because I was about to draw this in its actual geometry of trigonal planar. But at this stage I'm just drawing a dot structure, and it's more important to draw each one consistently so you can see the similarities and differences. Lewis structures do not need to represent the proper geometry. Right, so this one that I just drew, the focus is on that the right oxygen is the one that's double bonded. So now if you take the collection of drawings that I just did and think of them as contributions to an average picture, each one of the atoms is double bonded 1/3 of the time. So this one to the left is double bonded, single bonded, single bonded. It's double bonded 1/3 of the time. The one on the top, single bonded, double bonded, single bonded, double bonded 1/3 of the time. The one to the right, single bonded, double bonded. They each take equivalent turns at being the double bonded one, so that sort of averages them all out and makes their bond lengths and strengths look like they're the same if you take the collection of 3 resonance forms. And I almost left out a charge. The overall charge in each picture needs to be put there. So these are 3 resonance forms for carbonate, and each one of them taken individually makes it look like one bond is shorter than the other 2, but if you take them as a collection and average the behavior, you see that each oxygen is double bonded 1/3 of the time, so they're all equivalent. And you might be interested in knowing why did they come up with this theory, or what kind of evidence are they trying to explain. For carbonate, all three of the CO bonds are equivalent lengths, and all three oxygen atoms carry the same amount of electron density. So, and we'll talk about formal charges and how that's also an integral part of Lewis dot structures. But the three oxygens are equivalent, the three carbon-oxygen bonds are equivalent. If you look at a CO double bond, it tends to be quite short at 1.2 angstroms, so super short. If you look at a CO single bond, it's quite a bit longer at 1.41 angstroms. The CO bond length in carbonate is in between those two, 1.31 angstroms. So each bond in the carbonate, each of the three bonds, is somewhere in between a single bond and a double bond in terms of length and strength, and they're all equivalent, they're all the same length. So that's something that resonance is trying to explain, is that the carbon-oxygen bond lengths are all the same, and the picture we present as far as the bonding in carbonate needs to be consistent with that for the theory to make perfect sense. Right, the other thing we're going to talk about a little more is formal charge, which will be in another video. But the negative charge is also what we call delocalized. Rather than any atom having a full minus charge, the minus charge is shared amongst the different atoms, such that each oxygen is labeled with a minus 2/3 formal charge, rather than different formal charges on the oxygens being -1, and 0. We want all three oxygens to have the same charge, so the formal charges are averaged in the resonance forms, just like the bond lengths are averaged. So this idea of having a collection of three different forms for carbonate that average to create the total picture of what carbonate looks like is very important. And so hopefully this helps with resonance forms. And what I probably will try to do is create a few more examples of me doing dot structures and discussing the bonding and the resonance forms and the formal charge in each of the examples, because without a lot of practice it's really hard to know if you understand it really well.